All right, welcome to day 10 of Advent of Code. Used up all my fingers throughout the last, 9 days. Looking forward to day 10. I hear tell it's a toughie, so we'll see how it goes. Let's switch over to the code, and I've done the usual setup here that I guess now I've done a couple of days now in a row. We've made our files. I got our template file. I've got my blank input file ready to receive the copy. And we got our stopwatch. We've got our code line lined up. It's kind of funny, we skipped a bunch of lines here and we got some funny things. So we'll see how the page reveals itself. That's always fun. But for now, let's get to it. All right, so timer's on the move. Adapter array. Patched into the port, we discover weather forecast of a massive tropical storm. We're using the data from before. Okay, interesting. Before we can figure out whether it will impact our vacation, the device suddenly turns off. Its battery is dead. Oh, it's not what I thought it was. We gotta plug it in. What died? Is it our your device? I guess it's our little whatever we plugged into this seatback monitor. The charging outlet makes the wrong number of jolts. Always prepared, you make a list of all the jolt adapters in your bag. Each of the jolt adapters is rated for a specific output joltage. Okay, so we have a list of joltage outputs from each of the adapters. That's our input. Wow, this is a long description. All right, let's get that input. All right, so we have adapters of values that look something like that. Get our last new line edited there. And let's go back up. Any adapter can take as input 1, 2, or 3 jolts lower than its rating. Okay. So that's fine. In addition, your device has a built-in judge rated for 3 jolts higher than the highest rated adapter in the bag. Okay. Your device's built-in adapter will be rated for 12. Okay, so it's whatever the max is plus 3. Treat the charging outlet as having a joltage rating of 0. Okay, I'm not sure what that implies in terms of like compatibility, right? Because it's only 3 higher or lower. Since you have some time to kill, you might as well test all of your adapters. Sure. If you use every adapter in your bag at once. I'm not sure I understand what these adapters do. The distribution of the joltage differences between the charging outlet, the adapters, and your device. So the device's built-in joltage adapter would be rated for the devices. I'm a little bit confused with difference between the the charging. So there's an outlet, there's some adapters. I'm going to make a note here on the side here in our little handy dandy text file. Let me make sure I size this correctly so you can see it. Okay, so we have charging adapters, the charging outlet, which goes to the adapters and to the device. And we have these adapters, so the adapters are in the middle. The outlet is 0. And the device's built-in joltage adapter, at a glance here, 19 is the highest, would be rated for 22. The device is built-in, 3 higher than the highest adapter. Because adapters can only connect to a source 1 to 3 jolts lower than its rating, device adapters connect to a source, you need to choose them like this. The charging outlet has an effective rating of 0, so the only adapters that connect to it directly would need to have a rating of 1, 2, or 3. So we can make up to 3 jolt hops per thing. Of these, only one you have is an adapter rated 1. From your 1 jolt rated adapter, the only choice is your 4 jolt rated adapter, difference of 3. From the 4 jolt rated adapter, the adapters rated 5, 6, or 7 are valid. However, in order to not skip any adapters, you would have to pick the adapter rated 5. What do you mean not skip any adapters? Oh, we have to try all of them? Use every adapter at once. Huh. So wouldn't it just be a sorted list then? Assuming there's no gaps of greater than 3? Right? That's very odd. The next choices would need to be the adapter rated 6 and then 7. The only adapter that works with a 7 is the one that rated at 10, then 11, and 12. I mean, yeah, it's just a sorted list. There are 7 differences of 1 and 5 differences of 3. Okay, in this example, in a chain that uses all the adapters, find a chain that uses all the adapters to connect the charging outlet and count the voltage differences between the charging outlet, the adapters, and your device. So what is the number of 1 jolt differences multiply the number of 3 jolt differences? Let me go back up here 1 second. There are 7 differences of 1 and 5 differences of 3. So let me say 1. Oh crap. There's ones everywhere. The charging outlet has I think the outlet counts as 1. And then that's always a difference of 3. Okay, so we need to account for these end conditions. But it sounds like the first thing we need to do is pull in the input and sort it by, I'm going to make a separate file here because touch day 10 input small, just because there's going to be a lot of little things to kind of deal with. Like I need to play with these examples. We're going to have this parse on int. So we have a list of jolts, adapters, and then adapters dot sort. And let's see, that should sort ascending. Let's just print the adapters to make sure I didn't blow something up. I blew something up. I didn't paste anything into the file. Good job, me. Let's continue with this small one for now, the tiniest of examples. And so that's sorted. And then we say for adapter in adapters, we're gonna look ahead 1. So we'll say I in range len adapters at 0 is previous. We're gonna start the range from 1, and then inside of the loop we're gonna look at previous. We're gonna look at the current adapter adapters at I minus the previous value is the thing. Oh, actually, you know what? We can count previous as 0 because that's the source. So plug source, whatever you want to call it. So that'll give us that first set of diffs. Diff 1 and diff 3. We only care about those 2 differences, right? So then we can just say the diff is this, and we can say if diff equals 1, diff 1 plus equals 1, if diff equals 3, diff 3 plus equals 1. And then at the end we can do diff 1 times diff 3 and return that. Is that what it's asking for? And I know I need to do the last one here with the 22 situation. Oh, it's always 3. So we can just start it at 1. And then after 12, the only value is 15. And then 19. Let's try running this, see what it gets. We get 1. Good stuff. Let's see here. We go through each one. I didn't update prev. Previous equals now. Whoops. Ooh, what happened there? All right, run that. 35, which is 7 and 5. Looks good to me. Let's try the bigger small example. All right, there it is. Enter. run it 220, 22, and 10. That looks good. And now let's run it with the full set, 1876, 1876. And we're there. Nice. 925. All right. So I assume the hard stuff now is the second half, because that went pretty smoothly. To completely determine whether you have enough adapters, you'll need to figure out how many ways they can be arranged. All right. So this is where the bear is. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. I feel like if you could connect all of them, then they would, then I've determined that I have enough adapters. All right, all the different ways it can be arranged. Every arrangement needs to connect the charging outlet at a device. Previous rules. The first example supports the following arrangements. Yeah, and this is a useful way of representing it, putting a 0 and a 22 at the front, and the back and front, or front back, so that it kind of, then we can just churn through it and not need to do that awkward plus 1 minus plus 1 and off by 1 offset that we were doing. The charging outlet and your device's built-in adapter are shown in, yes, give the adapters from the first example the total number of arrangements. So these are all the potential valid possibilities. So this looks like another recursive tree search with kind of like that +3 window. So when we get to 4, it can either connect to 5, 6, or 7. So we see all the 5s, all the 6s, all the 7s. And then from 7, it's the 2 10s. Well, I mean, depending on which one, you still have to. So what happened to 6? Oh, you don't have to use them all. Okay, so there's the connect to 5, connect to, yeah, there's like connect to 5 and just skip over 6 entirely. There's the 5, 6, 7. And then, all right. But we still have to get to the end. That's the key. So it doesn't count unless we make it to the end. So it's like we can try to add, 12 after 6, but that's a dead end. So we say, nope, that's no-go. Okay. The second example has many more arrangements. Here are a few. That's quite a few. That many distinct. You glance at your bag, try to remember why you brought so many adapters. There must be more than 1 trillion valid ways. There must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device? The fact that it says this is a little bit concerning, because, the input only has, okay, let's say only has 94, but yeah, I get that it could be really, really bad. Still parse 1. We're going to take some of this code. Let's get this. All right, we got our adapters sorted. I think I'm going to write some helper functions here. We want, let's have an adapter class, which I'm going to, like, not an adapter class, but like a adapter list, adapter sequence. And what I want for it to hold is a adapters, right? I want these adapters in a list, and we're going to start with it, the source. Def init, and we're going to initialize a new adapter sequence with its outlet, and then we need some kind of def kind of finish adapter finish something. What's interesting is it's like 20. Oh, right, it doesn't have to be 22. Why did I think it was 22? Oh, just because the one was 22, right? And sequence, something like that, and it will return the self.adapters, but not after it first appends a whatever the last one was. So self.adapters at -1 plus 3. So that'll source, right? That's whatever the max was. Oh, you know, we can actually probably feed the max. Yeah, let's leave it there. We need a function to append stuff anyway, so let's do that, and we'll call that instead of doing this mumbo jumbo, which is a little bit questionable. Append, and we're gonna append a adapter, and we're gonna adapt that by doing what? We're gonna check the last value in adapters, and we'll call that last or prev. If a, because that's just gonna be a number, minus prev is greater than 3, or specifically, it needs to be between 1 and 3, right? 1, it can be 1, less than or equal to, less than or equal to 3. Then we're good. We can do the append of a. Else, print invalid append a. Let's also say last val current last value is self adapt. Ooh, not append. Adapters at -1. And when we append, should we return the whole thing? Let's not for now. Let's return nothing. And we need a way to get adapters, which will return self.adapters. So now with end sequence, what we want is not self.adapters append, we just want self.append. We're going to append whatever was at the end plus 3. What we should really do is when we we don't need to have it end on the same number every time, do we? No, we do. Maybe? I'm not sure. See, this is one of the things that was unclear to me. Because we're trying every valid combination. So in the smaller example here, 19... Okay, 3 higher than the highest rated adapter, and it looks like it's going to be all unique based on the way this is playing out. So that means that it will have to go to the end because it's pulling it out to 3. So that's good, I guess. We don't know what this is going to be at the start. So I'm inclined to say we still need something like this, unfortunately. Part of me wants to append the end sequence manually, just as another append at the end. All right, so let's not worry about that for now. And now we need a function to explore this space and do the branching appends. Whew, okay, so we need to... So the real question is there some way to calculate the combinations without doing, making this append sequence structure? Let's think about this a bit here. In terms of the way this math plays out, right? Like in the smaller example, we have a sequence of numbers, which I want to copy because I'm going to start with the smaller example for sure. Because even with the smaller example, I'm not convinced that I'll be able to sort this out correctly. So we have this, and we have these combinations. So this is basically the fully sorted list, and it's always 0 and 22 at the start and the end. So we don't really care about them in some ways in terms of combinations. We do want the combinations, right? Total number of ways, yeah, okay. So as long as we can calculate what that top value should be, we don't really have to worry about it. And so if we say that, we say at 1, the next value is going to be, anything from 2 to 4. And we see the only valid value is 4. So that means 1 valid, right? So then we go on to that 4. We say 1, 4. And the only valid values there are 5 through 7. And that means we take a look and we see what are the numbers that are between 5 and 7. We see there's 3 valid. And so then we say 1, 4. Now the question is, do we do 5, 6, or 7 here? Do we have to do all of them? Because now we're getting to a point where we're trying all the combinations. 1, 4, 7. Because we already captured that 3 number. So let's see where this goes. 5 then goes from 6 to 8. 6 can be 7 to 9. And 7 can be 8 to 10. So then we have between 6 and 8, we have 2 valid, right? That's 6 and 7. Between 7 and 9, we have 1 valid. And between 8 and 10, we just have 1 valid. And so what I'm trying to figure out is, does this multiply, right? It says the total arrangements are 8 arrangements total. And so what I'm trying to understand here is, because it looks like we see here 5, 6, 7, all 3 in a sequence. Well, I'm looking at the wrong direction, kind of, right? From 4, we have these two 7 7s, 6 6s, and 5 5s. But the 5s have 5 6 and 5 7. And that's sort of captured in the fact that this has 2. So there's 3 sets of 2 here, right? And then these 2 extra ones, which are 5, then 6, then 7. And I guess that is denoted in how these 2 behave, right? Because then when we go 5, then 6, then 7, we see that it's 1, 4, 5, and then 6, right? 6, and then 1, 4, 5. I know I'm just rewriting what it's already on there, but I think working through this is useful. So then the valid numbers are 7 through 9. The valid numbers here are 8 through 10. Okay, so 7 through 9, we have 1 valid. So what I'm seeing is it's sort of multiplication, but it might be like a sum of products. 8 through 10, we have again 1 valid, which is concerning. Maybe it's just the sum. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not good either. Okay, so how does this branching structure play out? Because the 3s and the 2s, these 2 clearly multiply pretty well. So this says there's 3 valid branches. And then those 2 have 2 valid branches. The other ones just have 1. And then those 2 valid branches, these 2, I'm trying to think whether I want to move these up. Let's try moving these up to here, right? So like this is one exploration of these 3 groupings. So these 3 valids led to 1, 2, and 3, aka 5s, 6s, and 7s, but then the 5s had the extra bit. And then beyond that, everything is the same, for better or worse. So it's like, it's just going to be more 1 valid, 1 valid, 1 valid, 1 valid as we go. Because 10 can go to 11 or 12. Oh, what? That's interesting. Hold on. Let me look back at this. And that's why these are doubled. Hold the presses. So these two are the same, 1, 4, 5, 7, 10. And then it's the 11 and the 12 that's causing a doubling. Like there's the presence of the 11 and then the absence of the 11. Presence of the 11, absence of the 11. So this whole 4, 5, 6 thing is really only generating 4 possibilities that get doubled by this 10, 11 flip-flop or 11, 12 flip-flop. And so, I'm going to copy this and cut out the extras, the dupes, so that we can see more clearly what on earth is going on. All right, let's do this. 1, 2, 3, 4, 5. Then we're going to go, go to the beginnings of each line. And we're going to go everything after 10 I don't care about. That did not work the way I thought it was going to work. Okay. This is where Vim could be helpful. 1, 2, 3, 4, 5. I could just repeat the 5 deletes. Thankfully, not too many examples to deal with. So we have 10, 11, 12. So the ones with 11 we'll keep. How about that? And we'll get rid of the ones without the 11s. Good. So, and I don't, whoa. Okay, so what are we seeing here? We have we have these two 5 combos, right? We said 5, 6, 7, 5, 6, 7, which is the 5, 6, 7, and then we said there's 3 valid, right, from 4. And so that yielded kind of these 3 basically. And then we said this one had 2 valid. So that 2 turned into these 2. So it became 3, but one of them counts as itself. So what? You have to subtract 1 on everything? Kind of? Because like we calculated this out to the 6, 7, so everything but the 10s, which is kind of what we wanted. Does this add up to 4 if you subtract 1 for all the elements? I mean, yes, right? Because this is 5 and then minus 1. That seems like a lame way to do it. How do you want to count these trees? Because algorithmically, I think I'm trying to figure out if there's a way to do this without having to go the crazy route of like building out the tree. Because yeah, I don't want to do that. And it's been a while, and I know I already wrote the class, but that's okay. So if at every position I check how many are valid, and then I go and explore each of those valid branches and see how many are valid looking a few ahead. Like I'm not going to look ahead at the whole thing, right? Because it's going to be sorted, and we're only going to look up to 3 ahead, right? Because they're unique values. So even if it's like we're on 4 and it's +1, +2, +3, like at most it'll be index 1, 2, 3 ahead. So we only need to look ahead 3 elements in a sorted list. And then we can figure out how many are valid and basically add kind of minus 1 of that to our grand total. The hard part is then we have a branching exploration problem, which is fine. We can deal with that with recursion. So at each level, we'll call deeper into the list. Can Python handle 100 frames of reference though? Like the full size input is a lot. So that part is a little bit concerning. But let's try it. Def count adapters, and we're gonna pass in something. And at each state, we're going. I guess we should pass in the adapter list. Adapters with an S. We don't care about the adapters that came before. So each time we call it, we're just going to call from the current position going forward. All right. And so when I call this I mean, down here it'll just be this, right? And it will return our count in theory. And then we can do, okay, this is like kind of a little bit like Fibonacci. We're counting ahead, count adapters of adapters at a certain index forward. So it's like whatever, wait, right now is all the adapters, and we don't care about, So there's a difference between the full adapter list, our bag. So let's call this like adapter bag. And then this is our like can append adapter. We might not need anything more than that. So we could say at any given state, we're going to look at adapters at 0. Between that value and that value plus 3. Right, that's the range that we're working in. And we can say value. I'm gonna loop through the 3 elements that follow the initial bit here. For value in adapters at and it has to be strictly greater than itself or equal to the plus 3 version. If, and so then we can say adapters at from 0, from its beginning, well, we don't care about 1 to 4 because we want to see 3 elements, right? We're gonna if we're on 4, yeah, click, okay. Or if we're on 4, if that's the 0th element, if this is gone, we can say plus 1, plus 2, plus 3. And so this is 0, 1, 2, 3, and then the limiter is 4. Then we can say if the value is, I mean, yeah, it'll be greater than itself because it's sorted. That's okay though, that's okay. The key here is if it's greater than it and less than the plus 3. For each of those instances, we're going to need to call out to count adapters with that value. Not with that value, with that value adjusted. Do I need the index? I think I want the index. So I'm going to enumerate that. And I almost forgot that was an option for a hot second. So what happened there? Adapters. Okay. Autocomplete, not holding up sometimes. And so we want adapters, because we're going to want adapters modified in some way, right? Like, oh, for each count, we just need to call forward and just count up how many times we can validly call forward. Like we saw there were 3 valid things to call forward on. That's all that matters. And at that point, if we, it depends on which one we withdraw though. Yeah. Because if we take the 6, just like, whoa. Okay. If we, like we saw here, when it picks up the 6, the 5 is gone. The 5 is skipped. So we need to account for that skipping behavior. So whatever the value is, right, at the location, that's going to be the new kind of root. So it's going to start from I. That's going to be the new start of our list. So it's like if we picked 6, then all of that vanishes. If we picked 5, like no matter what, this first one should go away. And let's make sure it does do that behavior at least. Yeah. And so it'll either be the next one. It'll either start with 5, start with 6, or start with 7, which is precisely what we want. And then each time it's going to append to that. Okay, so now we need the return bit. So we have a total, equals 0, total plus equals 0 to that, and total equals return total. So we're going to figure out each of those and then call down the stack until we get to the bottom. All right, what's the end state here? Eventually, we get to the end of the list. and we're not going to be able to call any further. So that might be as simple as if not adapters return 0, and that'll just append 0, count up zeros. Should we have an extra count? I don't think so. Yeah, we're counting combinations. The 22 or the whatever, the source plug doesn't matter. It's always going to go to that source plug. All right. Ooh. Yeah. Who saw that coming? This guy. All right. So very, very clever. Forcing us to use something other than recursion to solve this problem. But I am resolute in at least checking to make sure. What do you mean no input? Oh, I typed it wrong. Making sure our algorithm is reasonable. Are you kidding me? Even the small one? There's only 11. Ah. Drats. Okay, that suggests that I messed something up. Potentially. I don't know yet. But let's say, let's print out, let's print out this. Let's print out value. So we can see each thing being checked as it goes, so to speak. Aha! So it's a lot of force, and I am infinite looping. Good stuff. So what are we doing here? For adapters at I, enumerate adapters at 1 and 4. So then we call down, and if value is less than adapters at 0, so 4 is indeed less than 1 plus 3 or equal to 1 plus 3, then we add it to the count. This won't change anything, but 0. I is 0. Drats. Oh, interesting. It's because it treats it as it thinks of it as the actual kind of, we've resliced it, so it doesn't see the bigger picture. What we really need to do, since this is hard coded, right? I mean, it is essentially hard coded. Let's just get I in range 1 through 4 and call this range call correctly and put the in and say value equals adapters at I. So now we have a consistent language around what I and value should be. All right, we're out of range. That is a problem I can solve. 1, 5, 6, 7. Ooh, a little concerning that it's not checking the second one, but yeah, the depth first search. So when we get to the end, I need to deal with that problem first. So we're always going to the next one, and that's why it's falling over. So if there's only one element left, because like here we got to 19, and then we tried to count to 20, not 20, but the next thing, we already inserted 19. We've already gotten that count, sort of. And really it should be count adapters minus 1, right? Because every possibility counts as 1 less, kind of. So how about this? We can say if length of the adapters is equal to 1, then we will return 1 or 0. Because if we turn, well, let's see here. Let's see, in these examples, we found each time we've, you call adapters here, you say there's 3 of them, so we make 3 calls, and each of those, if they return 1 at the end, then we'll end up with 3. All right, I'm open to the idea. Let's see where it ends up putting us. It appears that it put us nowhere. Count adapters, like we're printing these numbers. Why is this not, oh, what the heck? It worked before, but not earlier? Adapters at I. Oh, it's still trying to go to the next thing. Why is that? So there's two things. Oh, we're trying to look ahead by 3 every time. We can't. So it won't. Okay. Let's call this end. End equals 4 or min of 4 or the length of adapters minus 1. And we got a 0. Cool beans. And we might manage not to get to 19, which is concerning. Okay. Because if we are at 1, it's never going to print 1, so we get to the thing. And then, all right, well, if we say instead, we'll, wow, that did not work at all. There we go. If not adapters, if we have an empty list, return 1, 0. That's not going to help us, but it's something. So the 12 had 2. Oh, that's an index. And we have the 7s. Okay, this all looks reasonable. Why is it not returning a number? Return total, return 1. Seriously though. Count adapters of adapters. Executes all that stuff. And we can say, how about this? Returning, oops, print, returning for, how do we signify which one we're on? Let's just put adapters. And is total. And I'm going to get, well, let's get rid of that for now. Aha. Yes, the returns are 0. Well, as they say, many happy returns. My guess is that it's not, let's print all of these. So my guess, let's go to the top, is that it's like searching through the one. Well, firstly, why is it going to 16 every time? And then doing all of this is not behaving the way I thought it was. Oh my goodness. I in range end 1 through 4. Adapters at 1. Oh, yeah. I mean, that's okay, I guess. But I'm a little bit confused as to why it's looping through all of this if I was 1 the whole time? Is range, am I using range wrong? Because that would be really embarrassing. Okay, that's what I wanted. And we see that here, like range is never bigger than 1. Oh, it's because of the recursive calls. So the first time through, adapters is, well, why does it say return? Oh, right, because we're at the bottom of the call stack. And so we're at 16, and so then the return for that is 0. Why is it 0? Return for 16.9. So adapters was 16, 9. All right, let's try it like this now. With length of adapters equal 1. So it goes through one more. Now that we've taken care of the edge cases, it's still 0, but maybe we can debug it a little further. So it's position 0, position 1. We are doing for range, the length is 2. 2 minus 1 is 1. So this will be 1. And range 1, 1, I believe, is nothing, is an empty list. So it'll skip this whole thing. Even though there's 2 elements there. Yes, 2 elements. Because we're already at 16 and we're seeing, is 19 within 3 of the thing? And we want that one. We want 1. It's because of that. I mean, yeah, basically. Because it needs to be 1 more. Right? Like we wanted 3, but it's 4. Yeah, there it is. Now that's some debugging. And so this return 1 is the key. As we get to the bottom and the accumulators hit, it piles back up, and it regrows, grows, and eventually you get that. Whew. All right, we're not out of the woods quite yet. We need to try the much more substantial input, right? Because this might still blow up our recursion stack and force me to rewrite this whole thing, or just get the wrong answer. Blast. 19,202, 10,976. Those are definitely not the same numbers. But hey, at least it didn't blow up the recursion stack. Kind of. Oof. All right, let's check this recursion stack real quick. I know the math is still wrong, but like, okay, it's computable. Oh, it's still working. Crap. Is it really? Oh boy. Okay, meanwhile, let's see what I'm doing wrong, because we got the simple example, but that was simple. Yep. Part of me thinks that it's some sort of like based on how many numbers are available ahead of it. Maybe you can go kind of greedy and jump all the way through ahead and say like, if the number is like here 4, you can jump all the way to 7 and just say that there's 3 and just have that be, a triple multiplier, whatever you want to call it, and then like something like that. Not sure. Let's look back at this. We have 3 valid options, and then we look at each of them, and each of them, one had 1 valid option, the other one had 1 valid option, and those 5 had 2 valid options. That's where the 4 comes from. It's 2 plus 1 plus 1. This 3 doesn't matter. That doesn't really help us. It still means we have to go through the whole branching structure. Times that I didn't take number theory. What is going on though? Like I'm looking at my task manager here, and Python's maxing out one of the cores, which is to be expected, but it is taking a while. I mean, this is not great. And I took away the print statements too. Part of me wants to kill it so I can look at the print statements. Part of me is nervous to look at the print statements because the recursion depth is going to be so bad. Wow, this is rough. So I go to each one, I count the adapters, I get them in. I think I need to fix it for the single case first. Man, recursion is so handy, and when you don't have it available to you, it is the worst. Especially with this kind of branching recursion, like we'll have to get a stack and manually manage it. or as Python calls it, a deck, which I used to pronounce as DQ for a long time. It's like, because there's a Q and then a deck, but the deck is spelled kind of similar to a Q. Wow, this isn't gonna finish, is it? Okay, oh man, I'm up against it, folks. I do want to know if this number has some special relative difference to the number I computed, which I guess is now lost because I'm not running this in a terminal. But it was like 10,000 something, which, you know, isn't a strict multiplier, but it could be something meaningful. I don't think I can run this. All right, let's stop. I don't know how far we got, but that was not good. All right, so there's that number. This is the number it's supposed to be. Whoop. Yeah, that definitely doesn't divide, or yeah. If it was like double or something, that'd be one thing, but it's like 8,000 and change off. It's like not a meaningful difference to like point out any bugs. All right, ready to print some stuff. Let's print some stuff. But like, how do we even debug this? Oh man. Part of me thinks I need to like have a bigger than the smallest example, but smaller than this gargantuan one. Wow. This is one of those times where you like step back and like reconsider your entire approach. With an input like this. And so we dig down. We go 1, 2, 3, 4, 7, 8, 9. So it hops through every one. And then returns 1. And then 47. Interesting. 47, 48, 40. I want to see if there's a 47 comma 49. Because that's going to be important. Because I'm expecting that to show up. But first it needs to unwind all of those possibilities first, right? So why is this 2? Is my first question. Oh, that's just I. But this is 2. So did the whole thing. We got to the end. This is the first one. And then it like went to the other iteration, so to speak. Like it went looped twice through. It's so confusing reading these because it's like backwards, right? So it's like, actually this one was printed, and then this one was printed. I mean, obviously because they're in order, but like I'm thinking about this, like this happened, then this happened, and then we returned a value and we went up a level. And up that level, we're still in this for loop, where apparently we went forward to this number, which I assume came from here. And so it went from 48, then it's like, also, there's 49. And that yielded a return of that, because I guess it was on 47, and it was saying we could be 48 or 49. That seems good. And then it's 48 or 49 is 2, and then it went up a level where it looped to the second 48. So 248, then it looks like it calls down a level, right? Whenever there's 2 in a row, it calls down a level. Back down to 49, that gets 1, and the return for 46, 47, 48, 49 is 4, which is the same as 5, 6, 7, 8. Then we call down a level, down a level, down a level. Then we have 1, 2, 4, and then the return for this is 7 somehow because reasons. Oh wow. So then we unwind from 48 back to 47 to 46 to 45, but then at 42 it doesn't increase anymore. And then minus 3, and then this is interesting. 38 and 39 are also 7s. I would have expected that to be a bigger count. So that's interesting, and may suggest something not quite right. You know, I'm thinking about this right now. If the value of itself is greater than the previous value and less than less than or equal to the value of itself plus 3, is that strictly speaking the same as their difference being 1, 3, or 2? Let's just check, make sure I'm not taking crazy pills here. If we say x is less than value less than x plus 3, alternatively we wanted x or less equal to. X less than or equal to value minus x less than or equal to 3. So we subtract x across the board. X less than v minus x less than or equal to x. Sorry, 3. And so we're saying it must be less than or equal to 0. So if we change this to that, then this needs to be plus 1 equal to. Yeah, let's do that. I know they're integers and it shouldn't make a difference, but it would make me feel a lot better. And hey, who knows, maybe the answer will be different. It's not though. It's not. Yeah, I didn't think it would be. But you know, this is the head scratcher, right? It's like, I think I might have to like rework through the whole thing. This totally explains why some people were like, I saw some of my other folks that are doing this. They got through the first question and they had a gray star. It's like, yeah, I hear you. Just take a gray star and walk home and leave with your soul intact. Oh man, I don't know. Like, yeah, this is rough. All right, so let's think about this some more. Maybe I can come up with some other examples. How's that? So this is too big of an example. The main problem is that you need to be like a example I know the answer to. Not only know the answer to, but like can make sense of. Maybe I can change how this outputs a little bit so it looks better, while simultaneously reworking it so that we have a way to not call this recursively, because that was terrible. Because we're appending, we're getting the adapters, we're ending the sequence at the end. You know, I could return true or false here. Just like a, you know, gut check of, did this work? And change this. So how would I do this? If I were to count adapters manually, right? Basically like try every combination. We're gonna initialize new adapter sequence objects each time. And every time we come across, I'm still thinking in terms of recursion though, that's the problem. Like every time I come across the, every time I come across a new thing to add, so let's do for A in adapters, we're gonna make a new adapter sequence at some point. right? And we're going to start it with a 0, and then we're going to append these adapters to it. And of course, that can't happen in the for loop. So something like this: sequence dot append a, and at the end we want to be able to, this is more just like almost practicing running the kind of running the class a little bit. Sequence end sequence. So these two come out, and we can return something like that, and we get our sorted list from 0 to 52, which is what we expected. Good. So now it's a question of, can we do every single combination of every number and try to make new adapters? So only in the outermost loop do we need like, we can be intelligent about how we're grabbing new adapters. I suspect it's because of this look ahead problem. Like, maybe if I just did this, there's no way this is gonna fix it. But hey, maybe it will. No, it doesn't. Okay. Yeah, didn't think so. So keep that 4, keep that commented out. So we can be intelligent about how we look ahead, and so we can say for each one we're going to build up kind of a kind of our existing various sequences, right? And each time through we'll try to append. We need a copy. That's for sure. We definitely need a copy, because we want to take an existing oh, I don't remember how to use copy properly. Yeah, I figured there would be a copy method, but I'm just gonna do it the silly way. Dot copy, it'll return a copy of itself. Yeah, so there will be no, do we want it to hold? Yeah, that's okay. So we call init. Okay, it's not going to return init. Self.init. Can I just activate the class itself? Adapter sequence dot init, and have that. Because I don't think I can do that. I don't think I can do this. Init on itself. No, that'll wipe out itself. We don't want that. Man, I don't remember how to make a deep copy anymore. Then we have to do for a in self dot adapters. Yeah, I know this is new a, and we're gonna do new a dot append a. This is an awful way to do it, come to think of it. Let's just make a straight copy of the list. New a dot adapters equals the existing ones copied, return new a. Not sure that'll work. I don't think I can access this from outside the class. Yeah, okay, we can cheat and adapter sequence and do it that way. And so sometimes we're going to need to make a copy. So every time we branch, we'll put a copy. The problem is we need to have the list of values. We need this list, right? And kind of like where we're at on it. This is just turning into the recursion problem all over again. So at each point along the way, like I still am not convinced I need this adapter sequence thing, but it may provide, like it just needs to be a list basically, right? Like I think we'll make a stack of the kind of existing adapters left and current adapters. So like adapters in the stack and then adapters that we have yet to kind of insert into our setup. And so I guess it's technically a deck. I haven't used a deck in so long. Yeah, so I think after an hour of doing this, this is the direction we're headed here. I think this class is gonna go to waste, unfortunately. Got a little bit overzealous with creating it, I suppose. All right, let's do this. Thanks for bearing with me, folks. This is rough. Current adapters left, and we're going to go through each one. I mean, it's a straight re-implementation of the recursion, and what I'm concerned about is that the recursion is not working correctly, which doesn't bode well, you know. So yeah, while dev, I'll call it stack. Deck. Oh right, we have to import deck from collections. Import deck. All right. Deck, is it deck? Yeah, okay. Call it a stack because that's what I know. Part of me wants to, I just want to run a quick little experiment here. All right, do I remember how to, what do we got? We can append, we can remove, we can extend, we can pop, right, we can pop left. But generally we'll be popping and inserting, no, popping and appending. Yeah, popping and appending. Rotate, oh, don't need that. All right, so we're popping and appending, we're appending and popping. We'll put in the first value, stack.append adapters at 0. We'll put that first value into it. Specifically, we're going to append 0. While stack is empty, all right, we'll just say while len stack, and then inside the stack we're going to, let me close this while we implement this bit here. What do we got? So that's basically our base case, and we're going to go through each one. I think we can keep this. Fingers crossed that this isn't where the bug is in my code. Actually, no, let's keep the total here. So we're going to go from the next thing to the end. Oh, current adapters left. So current adapters is 0. Can I put this horrendous data structure in here? It's a pair of lists. The first list is current adapters, which there will be just a 0. And I might make a little function to help us do this. So def get, I'm trying to think. We'll pass in the thing, we'll pass in the current, there's nothing, yeah, there's nothing to get here. Initial, this whole thing, just for clarity, we'll put the tuple and adapters. So we have the adapters. We're going to append the initial one, and then each time through we'll append some more. Yeah. So we'll take the adapters off the top of the stack each time. So we say stack.pop. And this will be our adapters for this iteration. And it will be adapters and current, right? Because it is a tuple coming off. And so we'll say that the current, see, this is the thing. Do we care about current? But maybe we do for this case, right? Like, so we're going to say we're going from 1, 2, 3 past the 0th position. So at 1, 2, and 3 of the adapters. Adapters at I, yeah, this is going down the same path as before. This is the concern, right? And like, is a stack going to be able to hold more things than the recursive frames? I sure hope so, but I honestly don't know. I mean, I think it will, because it doesn't have to hold it in memory necessarily. It can put it into swap space. So current is that. The end is that. So this goes from 1 to 3, or at most 1 to 3 at most, and then we're gonna get the value at that next spot, and we're gonna say if, but this time I'm gonna change it up a little bit, because I think what we saw here was that this value, oh, that's the problem. The value is at 1. Oh my goodness. No, wait, no, that's right. Yeah, because we set adapters at 0. So we manually held that back and made these 1. All right, we're still okay, but this should be the value, and we'll compare it to kind of base equals to adapters at 0. Yeah, so this will help make it clearer-ish, I hope. And so we'll say that the value minus the base needs to be less than or equal to 3. I'm going to write it this way instead. And less than or greater than or equal to 1. Right? So if this is true, then we're going to add this value, to the base, but we only want to add it temporarily. Yeah, I didn't take care of this removal problem, like when it skips. That's what I'm undercounting. Oh man, I don't even know what I'm... No, I am counting those, aren't I? Because I'm skipping ahead. Jeez, I keep thinking I found it, but I didn't. If the value is greater than the base, blue. And so, not base. No, that is value. Okay, so we have I, we have 0. So then we can say adapters. So then the adapters at the new set of adapters that are left is kind of 1 to the end. Well, I to the end, just like we saw before. And the ith adapter, right? That's what we want to put into our current. So if I'm keeping track of current, and current is a list, and so we're going to append current to the value. So for each of these, we potentially need to make a new one. So copy a new current. And adapter slicing, I'm worried we need a new adapters too. Like I think we're munging up the memory by, because we're passing by reference, and that's what's blowing it. So adapters at 0 is base. That's just the number. Adapters at I is just the number, but adapters itself and current itself is what's killing us here. So I think we need a new current. So current plus this dot append val. So I actually don't want the new line. So new current equals the old current, and we have this in the while loop. Man, it's been a while. New adapters plus equals adapters plus itself. New adapters at I through whatever. Oh, actually, you know what? I could just do this. Yeah. So that'll make a copy. I guess I could have one-lined the new current stuff too, now that I look at it. So these are the new current and new adapters. So then we can say new current, new adapters. So that's the tuple that we want. And we're going to add that to our stack. Stack add append. Tuple. All right. And something like that. Like this is the loose framing of it with bugs. Let me just glance at what I'm trying to not look at this too much because I'm worried that it'll mess me up. So when we get to the end, so now we're down to the base case. When we get to the end, the way we think about this is when we have just one more thing to add, when there's just one thing left in adapters here, right? When adapters is there's just one thing, then it's trivial. If length of adapters is 1, then there's only one possibility. And so whereas here we did a plus equals total count yada yada yada, here we don't return 1 per se as we come up. We're gonna increment it we're gonna add it to the total, which needs to be outside the while loop. This is gone, and this might still hold. Like, it's not return 1, it probably plus equals 1, right? So like each time we get to the end of a rope of adapters, a potential world of adapters, right? We want to add 1 to the set and continue on the while loop. We've already popped the stack. We found that there's only one thing left in the adapter, and for completeness, we can even do this whole dance. We can do current equals current append adapters at 0. You know that there's only one left, and have that get added to it. Oh man, I hope this works. Return total. Nothing left to do but to do it. Takes at most 1 argument, 2 given. What? Oh, does this tuple not work the way I thought it did? I guess I could wrap it in a list, but like that gets just ridiculous. Alright, just delete it. It's fine. Oh my goodness, it's the same answer. Oh, that hurts. That hurts a lot. Am I pasting this wrong? I mean, there's that possibility. I mean, it's more likely that I just screwed it up, but like, yeah, no, 10, 34, 3, that's right. 28, 33, blah, blah, blah. 20, 10, 28, 33, 18, okay. It's good to check. It's good to check. But here are a few arrangements. So one of the arrangements is, so it's really showcasing these where they took out those early numbers. I wonder if that's suggestive of something, right? Like 48 is gone. Like, and what are the exact combinations? I know we have 10,000 of them, so it's like, but what happens if we do this one? Do we get 8? I mean, based on our formula from before, it works. And are the 8 the right 8? I think that's also potentially worth exploring. The code's faster though. Give it to that. Print new current. I know print is spelled wrong there. So there's our supposed 8. Our fabulous 8. Are these 8 unique? No. Why is there a 1 there? Oh, that's just from printing the full list. Oh. I'm not adding the 1. Oh, wow. Because of the way the look ahead works, I'm grabbing from the base of adapters, not the current. Right? I'm skipping the first one. I'm missing an entire tier at the top of my tree. And so I'm grabbing from the current one here, base. Base shouldn't be adapters at 0. It should be current at -1. Why isn't current auto-completing? Probably just because of the mess I've made back here. And now we get 0. Current at 1, adapters at 0. All right, so now that it's iterative, maybe we can see what print current, print adapters. So current is there. Adapters is here. Why did it end? By changing all I did was change that one line. If the length of adapters is 1, the length of the stack is, so we go into the thing, we print these two, sorry, we print these two, and then we start working on this for range based and adapters at I. Why isn't this working anymore? Well, because we set base to 0 now instead of 1, and so it's too far away. And so we don't want to look at range 1 to n. We want to go from range 0 to n minus 1. Still end. Never mind. Take that back. And we want to still look at 4 or 3? 3 now. Because it used to be 1 to 4, now it's 0 to 3. Now we have 6, so that's not right. So I think I need to print both of these. All right, we're getting somewhere though. We are definitely getting somewhere. All right. So at the beginning, at the start of it all, Our current is that, our adapter is that. We put the 1 to the thing, and our adapter is that. Ah, not quite, right? We don't want, we never want this overlapping behavior right here. So after the first loop through, right, the first time through we have this, then the second time through, we haven't chopped off that first element. So there's still some adjustments to be made here. Because now, in this new world we're in, we are considering taking off, I think, I plus 1 potentially values, because index 0, 1, and 2 are the candidate things, right? And so we lowered everything, so all the hard-coded numbers need to be shifted by 1. I mean, not these numbers, but the other numbers. And I think I've got them all at this point, but I had missed a few. All right. Fingers crossed. Please be different. Oh my goodness. Nothing. Nothing. All right, so I think we have a little overlapping problem with the conclusion of each one. Oh, it doesn't even go to the top anymore. Jeez. Adapter, and we always do adapter after current. So current, adapter. Oh wow, we're like very far into it now, aren't we? All right, so if the length of adapters left is 1, what are we doing? We take that adapter, we put it on current. We've already popped the stack, so we're not putting anything new back on the stack. What I'm confused about is why would we ever have a case where the adapter being popped off the stack would be empty? Because if there's nothing on the stack, I mean, if their length was 1, we made a new, we moved the current to, we appended the only value in adapters to current, and we printed it out. And once we have it, we add our total. And like it really seems like I've got some kind of weird boundary case issue here. Current, then adapter. So current, then adapter. So that looks right. It's just that there are some cases where they are overlapping, especially the ones, these empty ones. How did it get like that? Okay. I assume it's because when we sliced I plus 1 to the end, it yielded an empty one. And so then it goes back through. It won't be this. Oh, and then we miss a count. Right? We miss a freaking count. Basically. And there's still this weird overlap, 14 and 14, 17 and 17. Oh wait, no, it's current and then adapter. Current and then adapter. I really need a new line here. I know it's going to kill our print queue, but it needs to be done. Where is it? Or at least maybe we can tab in. That could work. A current and then adapter. Nice. So, and we could say at the top of each, after each thing, if current at its end is equal to adapters, adapters at the end equals what's left. Which one's which? The current at the end is either, oh jeez, I'm losing it. Is the first element of adapters. Then we say overlap. And then, and only then, do we print. Let's take a look at the overlap cases. Oh, good on me. Okay. If adapters. Oh, I put two ifs. Ooh. Uh-huh. What is this print statement doing? But seriously, what is this print statement? Oh, print new current? Yeah. Oh, there is no overlap. So this was just all of the values that we made printed out. I do want to know. Combos. And let's make that a set. And do combos add new current. And at the end here, unhashable type list. Fine, be that way. Okay, they are all unique. That's good. That's good. I wanted to check that because that's the sort of thing that, you know, would have been really concerning if somehow it ended up being not unique, but it was possible, you know, like it could have happened. I'm going to take that away. I'm going to take this. Oh, whoops, not this way. I'm going to say return here because there's overlap. So we're good here. Current and adapter, current adapter. I want to see the beginning of this bit here. How should we do the beginning? Sort adapters, print adapters. Let's do adapters equals adapters. Let's get the first 20 values sorted there. And kind of see how this plays out at the start. So we have this 1, 2, 3, 4, 7, 8, 9, 10, up to 32. Then we have current and adapter, current and adapter. So somehow we got to the 3, and then I hope we do the 1 and the 2 at some point. As happy as I am ish to see the values working out here. And really the current, the first of the adapter needs to be not only equal to, but strictly larger than, adapter needs to be larger than current, if there's any value. And so I'm trying to get all the 3's done. I want to see if we get a 2, 0, 2. Okay, I'm going to scroll this because this is getting to be... Alright, so there's 0, 2. I think I found the boundary-ish. Here. So we have all the 0, 3's. So it does the full depth of that. And then it goes over and does the 2's. And it does the full depth of all the different combinations of 2's. And then it does all the combinations. Eventually, oh my goodness, of 1's. Right? Current, I have a lot of 1's now. Getting there, 1's, oh, back to 2's. 1's, 1, 4, 1, 4, 1. Okay, here. Current and adapter. Current and adapter. So this doesn't, I mean, this looks fine. 0, 1, and then within 0, 1, it could be 2, 3, or 4. It's a little bit weird that it's going from the biggest to the smallest, but that might just be, oh, right, because it's in the nature of the stack, because it's going to go we're gonna append, and then yeah, I could have made it a queue, right? And there's consideration of whether I want to do a queue just to get the numbers to like be in order to make it easier to debug. And I do want to run it on the full input. I know it's not going to be right, but just for the purposes of like ensuring that this works and can, oh, overlap. How curious. Okay. That I can work with that. Oh, overlap right away. Oh no, not right away. I mean, we went through a bunch. I'm curious also then what is the total at total 0. Cool. Part 2 input, what? Oh, because we're still cutting the input down by a lot. That might be a good thing, just in terms of like that tells us something, right? Like where is it? If adapters at 0 is greater than not if it's the other way. All right. It's a number, don't know if it's right, and we need to take away that limiter here. We're still printing a lot of stuff. Probably should take that away. I'm gonna stop that for the sake of the printing. All right, so this is a non-recursive approach. Oh man, it's very possible that I'm gonna have to come back to this and I don't know, go for a run or something and just like think about the mathematical underpinnings here, because I've taken away the recursion problem. That clearly isn't the issue, and the bigger issue, of course, right now is that I'm still not getting the right answer, which is how on earth? Distinct arrangements. Yeah, no, those were distinct arrangements. We checked. And they've got more distinct arrangements than I do. It's kind of crazy that I got the same number multiple times, though. Even with all those adjustments. That's crazy. So, Python is working hard, trying to crunch this out. Let's put a little limiter on here. Let me do total. It's just some more diagnostic stuff. If total modulo, I don't know, 1,000, 10,000 is 0, print total. Anything else I want to print? Maybe current and adapters. Apparently that's the thing to print these days. Oof, that did not work. All right. So every 10,000 iterations. Oh, wow. There's a lot. I mean, the thing did say trillions, you know? Crap. I can't even keep up with this, the rate of this thing going. All right. So let's scroll to the end here. So it's building to 145-ish. We're ending at 148, which doesn't seem like a crazy number, but we just check to see if there's a 149, 150, 151, 152. Okay, so 148 is the largest of my inputs. Part of me is concerned that, I mean, the last value should never matter, right? Like this is strictly there to ensure that we don't What is it there for? I would have expected us to overcount if we ended on 48 and not 49, for example, right? But at the same time, we can put it in. Like, what are we at now? 9 million? I mean, they said literally trillions. Like, holy crap. Okay, so 1,000, 1 million, 1 billion. I mean, we got to 9 trillion. We should probably not be billion. How about million? 10 million? I got the 9 million. We'll leave it at 1 million. That's fine. The bigger point here that remains is that we're going to put in our first value. That's, I think, reasonable. But what I want to do is after we sort, I want to append, not adapters. It doesn't return a value. So append 148. No, 152. No, 151. Whew. I guess really what I should be doing is max of adapters. And so once we have that, and then I want to do the small test again. So let's just leave that there and add this to small. Are you kidding me? That made it work? Wow. Wow. Okay, now it's just a matter of time. I made it work. That is redonkulous. All right, so we got our 1 billion or 1 million setter. We've got our file lined up. Let's run it. I'm going to consider this done, basically, because if it worked for such a big input and I nailed the number on its head, and I don't know what else, I can do, right? Like, I don't know why this is printing so many times. That part is concerning. In particular, all these zeros. Yeah, why? Oh, just because as it's getting set up, it's... Wait, why are there so many zeros? Oh, it's just going down the stack. Okay, so it's going to be a while before it... And it prints 2 million over and over again? Huh. All right. There's like no new totals to be added, I guess, because we don't always increment total. We only increment it when we get to the end of the loop, So it goes. But I think I've got it. I mean, I got this intermediate value correct with what is 19,000 distinct arrangements across however many lines that was, 31 values. Ooh, so we'll call it there and call it good. Been almost 2 hours here. Thank you for sticking with it, those of you who have it in the background while doing something else. And yeah, we'll see you tomorrow, Friday, for the day 11. And I will definitely, after I hopefully get this done, be taking a look at what a more effective solution was. I bet you there's some really clever combinatorial approaches here around just multiplying some numbers together rather than what I've done, which is effectively brute forcing it. Yeah, gotta go brush up on my combinatorics and number theory in terms of, I was kind of going down this path with these, but like didn't really suss it out. But yeah. I'll see you tomorrow. All right. Have a good one. Take care.